Suppose the inter-arrival time is constant. Then the Laplace-Steelges transform will be e power minus theta. You can find the limiting distribution for the DM1 model also. When the inter-arrival time is a constant, then the corresponding queuing model is denoted by DM1Q. So we can find the limiting distribution at the arrival epochs as 1 minus psi power j, where psi is the root of the equation, psi is equal to e power minus mu times 1 minus z, because psi of theta is equal to e power minus theta. So to get the root of the equation, you have to solve z is equal to psi of mu minus mu z. You have to get the root of the equation, z is equal to psi of mu minus mu z. So in the DM1 model, psi of theta is equal to e power minus theta. Therefore, it will be z is equal to e power minus mu times 1 minus z. So if you solve this equation, you will get psi, that is a unique root between the interval 0 to 1. Substitute psi here, so that is the limiting distribution at the arrival epochs of DM1 queuing model. Now we move into the multi-server queues. The embedded Markov chain analysis of the queue GIM1 can be easily extended to the multi-server queue GIMC, where C is the number of servers in the system. Since the number of servers are greater than or equal to 1, the one-step transition probability matrix will be different now. That means each element Pij will be different from the GIM1 corresponding one-step transition probabilities Pij's. So here we can consider three cases for the initial value I and the final value j. So corresponding to the each cases, your Pij can be obtained. For the case 1, I plus 1 is greater than or equal to j, greater than or equal to c, you will get Pij in this form. This represents I plus 1 minus j service completions during a inter-arrival period when all C servers are busy. So the case 1 is related to all C servers are busy, means the number of customers in the system is greater than or equal to C. That is a situation in which you are getting the one-step transition probability for the embedded Markov chain. For the case 2, the I plus 1 is less than or equal to C, whereas j is less than or equal to c also. This case is related to I plus 1 minus j out of I plus 1 customers complete the service. The third case is related to I plus 1 is greater than c as well as j is less than c. This represents I plus 1 minus c customers complete service with the rate c mu. Then c minus j out of c customers complete the service. To get the complete limiting distribution at the arrival epochs, you can refer Gross and Harris to get the complete result. So here we have discussed only the one-step transition probabilities, how that is different from one-step transition probabilities of GIM1 model. Now we move into GIM1N queue. So this queue is similar to GM1, but now the system capacity is restricted to some finite number capital N. Therefore, the relations between Qn and the Qn plus 1 will be a smaller change in it. That is, a Qn plus 1 will be minimum of Qn plus 1 minus Xn plus 1 comma n, where Xn plus 1 is the number of potential service completion during the inter-arrival time period. So once you know Qn plus 1 in terms of Qn, we can conclude, since Qn plus 1 is in terms of only Qn and Qn plus 1 is independent of Xn plus 1, therefore Qn form a time homogeneous discrete time Markov chain, and one can find the one-step transition probability matrix P with the entities Pij's. Here also you can verify the row sum will be 1. And each Bi is nothing but the probability mass function of each Bi's are nothing but the distribution of X. Once you know the one-step transition probability matrix, we can go for finding the limiting probabilities. Note that the last two rows of the matrix P are identical because of the Markov chain effectively starts off with the n customers from either of the states n minus 1 and n. Therefore, if you see the last two rows of the transition probability matrix, both the rows will be identical because of the Markov chain effectively starts off with the n customers from either of the states n minus 1 and n. Since the finite state DTMC is irreducible, aperiodic and positive recurrent, then the limiting distribution exists. So let pi be the limiting probability is defined as pi j is equal to limit n tends to infinity Pij of n. We can determine the limiting distribution by solving pi is equal to pi p and the summation of pi a is equal to 1. Here there is no restriction on rho because it is a finite state Markov chain. At the end, we move into GI-G1 queue. In this queuing model, a single server queue with the arbitrary arrival process, that means the inter-arrival time or non-exponential distribution, and arbitrary service time distribution, that means the service time is also non-exponential distribution, with the infinite buffer. Let S be the random variable representing the service time, and the expectation of S will be 1 by mu, where mu denotes the service rate. Let lambda be the mean arrival rate. Assume that lambda is less than mu so that the queue is stable. For a stable system, you need lambda is less than mu, where lambda is related to the mean arrival rate and mu is related to the service rate. One can show that for a stable GI-G1 queue, the utilization is given by lambda by mu. Utilization is nothing but what is the probability that the server is busy. So that is given by lambda by mu. We are interested in the distribution of number of customers in the system, in the limiting distribution. We are interested in the limiting distribution of a number of customers in the system. Let Pn be the probability that there are n customers in the system in a long run. The probability that the system empty is given by P naught, that is nothing but 1 minus utilization. The utilization is given by lambda by mu, that is the probability that the server is busy in a long run. Therefore, the probability that the system is empty in a longer run is same as 1 minus utilization, that is 1 minus lambda by mu. Note that Little's formula can be applied to obtain the average measures such as mean system size, mean queue size and mean delay. Since it is a stable system with the lambda is less than mu, you have the probabilities, and once you know the limiting distribution, you can use the Little's formula to find out the all other average measures. That means using the limiting distribution, you can find out the average number of customers in the system in a long run. Once you know the average number of customers in the long run, with the mean arrival rate lambda, you can find the average time spent in the system. Once you know the average time spent in the system, you can find the average time spent in the queue also. And once you know the average time spent in the queue, using the Little's formula, you can find the average queue size also. So, using Little's formula, with the help of a limiting distribution, we can find the average number of customers in the system, then average time spent in the system, average delay and average queue size also. So, in this lecture, we have covered the non-Markovian queues, namely GIM1, GIM1N, GIMC, GIG1 queues. With these 5 lectures, the renewal process is over. Here is the reference of renewal processes.